for one hypothesis. You pick a delta, you pick an
Uh,
epsilon, and that's how many examples it takes to learn one hypothesis.
Sure.
And if you were learning more than one, you'd have to give it that many examples of that hypothesis again.
Why do you need more than one?
Like for example, if you're trying to learn, if you came up with a number of examples to learn one design out of all the assemblies that you could possibly have, but you wanted the machine to identify every design, you'd have to give that many examples of each design again.
Yeah, that's probably right.
Okay.
So if your concept changes,
Yeah.
that means all the labeled examples change.
Okay.
Potentially, you could relabel the existing data. Potentially.
Okay.
Other questions? So how's this homework been in general? I mean, easy, difficult, just so that I get an idea of how things are.
Confusing.
Confusing. Is it because the concepts are confusing, or is it because the text is confusing? Both. And okay, yes.
I'd say I felt like I understood the concepts really well until I started doing some of these problems.
I agree.
And then I got really confused.
Okay, has that been fixed? I mean, is there anything we can do? Yes.
And there are some questions that can have more than one answer, or many students think about that differently.
Yeah, so you need to justify your solution. I mean, if at grading time we feel that what you have is correct. So for example, let's take one of these VC dimension questions. I don't remember the questions themselves, but there are a typical thing in computational learning theory, usual homework / exam question in computational learning theory is you're given some tiny little hypothesis class and you're asked what's the VC dimension. There's only one answer. If the VC dimension is 18, the VC dimension is 18. It cannot be 17 or 16. So there's only one answer. Now, the thing is, even though the answer is unique, there are multiple ways of getting there. So there might be multiple proofs. And there we have to, that's why this is the hardest homework to grade. We have to read your proofs and figure out if you have the right argument. And this has to be formal mathematical proofs. So, you can't argue your way, you have to prove your way. That said, there are some other questions where, let's take the last question in the homework. It says if one hypothesis space is contained in another, VC dimension should be less than the other. You can prove that in multiple ways. Again, you might be able to get the statement that you're proving is fixed, but you can prove that in multiple ways. So yes, there are multiple possible answers for that. One of the nice things and annoying things about this homework and this general, if you're seeing this for the first time, is exactly what you said. It might seem like the concepts are easy to understand, but until you actually start applying these ideas to something, at that point you really have to wrap your head around the basics. One thing though, I have noticed, and I tried solving this homework the other day, I noticed that nearly all the theory questions can be answered if you just start from first principles, apply the definition, and just go methodically from the definitions. So for the VC dimension questions, we did a few examples in class. You have to basically do the same sort of, the thought process should be similar. You try out 3 examples, you try out 4 examples, you try out 5 examples, and imagine there's an adversary who's labeling it. Try out every possible labeling. And at some point you'll be able to get to a number where you're not able to, there is a labeling for which you're not able to find a function. Now you need to generalize that argument. You need to prove that it's not just this one set of examples, but any set of examples have that property. For the VC dimension, so for the proof questions, I think in all cases you just have to go from first principles. Just apply, take the definition of whatever you're proving, and typically the answer just follows very quickly from the definition. Of course, it's not literally just writing down the definition, it's mangling the definition away. Are there specific questions? Other questions? Any questions? Yes.
For first problem, when you said we can, for each part, we can cut it into two different pieces. When we want to use those equations, it means that now, if we have 6 different part numbers, we can, in fact, the number of parts is 12 or just 6, because.
So let's take, so I think this question came up in my office hours also. So let's say you have 3 parts, A, B and C. And let's say you've chosen to, just to create one product, you've chosen to break B. So now you can use, in fact, you have the option of breaking any of these. So let's say you break A, you get A1, A2. You break B, you get B1, B2. You break C, you get C1, C2. Now you have the option of not using A, or using the entire A itself without breaking it, or using one of those components. Similarly, you have a similar choice for each of those segments. I hope this has given you a big hint.
Yes.
Okay. Yes.
On the forums, it was saying,
Can you speak up?
on the forums, it was saying you didn't have a similar choice between both of the components because you couldn't choose both B1, B, and B2. You could only choose B1 or B2.
Oh, instead of choosing both B1 and B2, it's as if you're right. You can't choose, let's pretend that you can't choose both B1 and B2, but you chose not to break B. So your options are nothing, B without breaking, or B1 or B2. Is that, Jay, is that consistent with what you've been writing with? Yes.
Yeah.
Yes.
So you said we have to prove for each of the VC dimension things, like how we got the number.
Yes.
So can we just prove by that labeling thing that you just said? Like,
Yeah,
that's
yeah.
how we've gone about it, like saying that if I take this, then this is how I will get a label.
So every VC dimension, or not every, but typically VC dimension proofs have an easy part and a hard part. The easy part is the lower bound. I'm actually generalizing here, but at least in the examples that you see in the class, the easy part is the lower bound, where you will come up with a set of points, and you'll just enumerate, for example, all the possible labelings of those points, and you'll say that every possible way that you can label it, here's a function. And the way you produce the function is actually, in most of these cases, you can just produce the function. The hard part is the upper bound, where you have to argue that here's a set of points that can be adversarially labeled. Sorry, here's not a set of points. For any collection of these number of points, there's an adversarial label. And then in that case, the goal is not to produce the function, but to construct an adversarial labeling for any collection of points. So you need to say, how do you label these 14 points adversarial? Now, I'm not that cruel. I'll not ask you to enumerate every possible thing from 1 to 14, but that's also a hint. Yes? Yeah.
So on, I think it was 2.2a, is the one that says you have all Boolean functions and there are k that are essentially
Right.
positive. But what I'm confused is, if you're forcing k to be labeled positive, then where's the adversary in this?
Which case?
Sorry, what's that?
So the adversary is not labeling the points. The adversary does not get to pick the function.
Okay.
The adversary gets to label the points.
Right, so say you had 3 points and
Let's take an
k was
example.
3.
Let's take an example. So let's say you have 3 dimensions. These are your possible inputs, right? This is all possible booleans, combinations of 3 booleans. Now, let's say that k equals 2.
So these are the labelings of
No,
3
these are the points. These are the x's. This is x1, x2, and x3. These are your 3 points. So here, this is the entire instance space. I'm actually listing out the entire instance space because I want to list out every possible function. One function might, let's call that x naught, would label, so let's say k equals 2. One function would label the first 2 points as positive and everything else. So let me use plus and minus. Plus, plus, This is a function, right? This is a function that's in the set. Another function, h1 would label the first one as positive, and so on. So you have exactly two positives at any point. So you'll have another function h whatever h8 would be 0, no, sorry, a plus, a minus, plus, plus, something like that. So there are many such functions. Now let's say, now you have many such functions. Now let's say I have the input is, let's say the set of points has only one element. Let's pretend, just for the sake of example, this is not a valid proof, let's pretend that that set is this collection of these 3 points, these 3 values of x. This is equal to, this is your set. Now, let's pretend the adversary labels this as a plus. Can you find a function that agrees with this labeling?
Sorry, say that again.
Can you find a function that agrees with this labeling? Was there a function that labeled this point as plus? Of course there was. Was there a function that labeled it as a minus?
Yeah.
So your VC dimension, this is not a valid argument, but this is, in this case, the VC dimension is more than 1. Actually, this is a full argument for VC dimension for this case being more than 1. Okay, now let's just consider, and again I'm giving you proof by examples. Let's say the set consists of 3 points. Can you come up with labeling of these points such that there's no function in your set of functions? All positive. Because your set of functions was restricted to, so let's say that the labels were all positive. The correspondence is 1 to 1. Now, remember your set of functions. Your set of functions allowed exactly 2 positives. So this cannot be in this labeling, there's no function in your set that agrees. So here's an adversarial label. Now generalize this to arbitrary cases. Yes?
So my question is regarding, on the forum somebody said do not look at the order of x for part A.
Do not look at the order of x. What does it mean?
So we were told that x is a finite set.
X is a finite set. In
Yes.
fact, x is Boolean hypercubes.
Right, which means that if we were to choose k equal to the order of x, all labels would
You mean
always...
the non-side of x?
Yes.
Yeah, sure.
So we would then get all labels were always positive.
How many functions are there?
1.
Yes.
And this function would obviously have VC dimension of...
Right. So that's a subtle technical argument.
So my point is that there is a bound up towards the top, which means that...
Yes, you're right. There is in order to complete the proof, you need to, the VC dimension is more, so you can ignore that argument for this.
Okay, so that was my question.
Yeah.
Were we supposed to look at that or not?
You can ignore it, if you write it, the TS will appreciate it.
Okay.
Other questions? Yes.
So in lecture, when we were talking about the Hofstadter bounds, we said that formula we derived was saying there exists some hypothesis
Right.
that satisfies this. In the homework, is in part the preamble to the Chernoff bounds, it says that formula applies for every hypothesis. I just want to clarify which one of those is correct.
The formula applies, which formula applies for every hypothesis? Do you have the...
The m is greater than 1 over 2 epsilon squared times log h plus log 1 over delta.
Right.
The slides say it's for any...
there exists. There exists.
Okay.
I saw a hand here somewhere. Someone raised half a hand in there. Was it you? Okay. Alright, there are no other questions. I'm going to move on. Other announcements, there's a project intermediate report that's due on November 8th. I hope you're working on that. Homework 5, because you guys are so eager for more, will be probably available late today or most likely early tomorrow. Homework 5 will cover support vector machines, largely. And those of you who are missing decision trees will have an opportunity to revisit them, because your decision tree code can be revived. We'll train decision stumps, actually depth limited trees of size 2, and then use those as feature extractors for training a support vector machine on top. In other words, you'll be training an ensemble of decision trees. I'm traveling Thursday, so there'll be a guest lecture. My student Jingwan will talk about stochastic gradient descent for support vector machines. Please don't miss that lecture, because that's basically your homework. And in fact, stochastic gradient descent is generally an important concept to learn. Any questions about any of these things? Going once, twice. Alright, so let's continue where we left off. We were in the middle of boosting, and I'm not going to repeat the algorithm, but just to give a flavor of it, boosting was a way of constructing a strong classifier if you had a weak learning algorithm. A weak learning algorithm was an algorithm whose error was only slightly better than chance, only some gamma less than epsilon, less than half. And add a boost was this constructive proof of the following idea. If a concept is weakly learnable, meaning there is a weakly packed learnable, meaning there's a packed algorithm that has whose error is just slightly better than chance, then the concept is strongly learnable. And the proof for that was this algorithm called add a boost. And the way add a boost functioned was it set up a weight or importance for each example. Initially, every example was equally important, and then you learned a weak classifier and an alpha parameter, a weightage for that weak classifier. The picture is something like this. You learned a weak classifier and an alpha for that, and you kept doing this, and then after that you reweighted the example so that the examples where the previous classifier made an error become important in the next round, and then you repeat the process. And AddBoost has this pretty awesome theorem associated with it, which says you run AddBoost for t rounds, and at each step the weak classifier has an error epsilon t, and epsilon t is just 1 minus gamma t, which means it's gamma is a small number, positive, which means it's half minus gamma t, which means that epsilon is slightly less than half. Let's just assume that the smallest of these gamma t's, is this number called gamma. The training, then, if you run AddBoost for t rounds, the training error of the final classifier that you construct as a linear combination of your weak classifiers is less than e power minus 2 gamma square t. Important thing here is e power minus t, which means as you run AddBoost longer, the training error exponentially decreases. And one way of thinking about this is, if you have a weak learner, you can boost it into becoming a strong classifier. You can boost it into discovering a hypothesis that makes very low training error. And I encourage you to look at the proof on the class website. Yes?
So why are we using weak learners? Why don't we just do a conglomeration of strong learners?
Oh, this is true for weak learners, which means it's true for strong learners as well.
But would you get a better result if you used all strong learners?
You might end up overfitting. So you have to be careful. There's no, you don't get something for free. In some sense, this algorithm changes the hypothesis space. Your H final is not in the original hypothesis space of the weak learners. That's one reason. Another thing is, not often, but sometimes it might just be easier to train a weak learner. A rule of thumb. You might be able to create rules of thumb programmatically in an easy way, but you don't want to think about, creating a strong learner. So the training error decreases exponentially, and empirically, this is, I think this picture might be from Tom Mitchell or Pedro Domingos, I can't remember, but very often you see this, the training error goes down to 0. You end up overfitting the training set, but each week, but the error of the week classifier as the round iterate goes up. So you get worse and worse weak classifiers, but their aggregate becomes better and better. Which seems counterintuitive until you realize that there's an alpha that controls how important is this weak classifier. Those alphas get smaller and smaller. So you're basically kind of getting, you're fitting some little noise in the data probably. But we know that training error is not the important thing to do. Test error is the right one. And you've seen some pictures like this before where the training error goes down but the test error eventually goes up. This is like the classic picture for overfitting. And in an ideal world you would like to stop here, but you don't know where there is because you don't have the test set. In some sense, if you run AdaBoost for too long, the theory tells us that the final hypothesis will become so complex that you end up overfitting the training set. You end up losing out in generalization. But in practice, there's an intriguing observation on some data sets. This is completely empirical. There's no, I'm not making a more general claim here. This is just empirical. The training error goes down to 0 and the test error does not go up. The theory tells us that the test error should go up and the test error seems to flatten out. And there have been some attempts to explain this. One of them was this paper from '97 which showed that AdaBoost under some constraints ends up actually finding a linear classifier that maximizes a margin, that tries to find a large margin classifier. We'll talk about large margins in a bit. So this is just a connection. So let me wind up this lecture on AdaBoost. It's a very simple algorithm. All you need is a weak learning algorithm that can take into account the distribution over examples. If you have that, you can always you can boost it into becoming better. You can use it with any weak learning algorithm. It does not care what your weak learner is. All you need is something that finds classifiers that are better than chance. That's the good news. The bad news is the performance of the final hypothesis often ends up depending on the weak classifiers that you use and the data set that you have. If your weak classifiers are too weak, then you end up underfitting. If your weak classifiers are too strong, you end up overfitting. And what's the sweet spot? I don't know. That said, there is actually some empirical evidence from about 2005-6 from Rich Caruana and a student who showed by running massive experiments on like hundreds of data sets using hundreds of learning algorithms. Think of it as like a weak version of your class project. A stronger version of your class project, a much more rigorous version of that. By using hundreds of different data sets and classifiers, they found that if you have smallish number of features, then boosted decision stumps are an excellent thing to try. And because they end up being like among the best general purpose classifiers. This was 2006. Since then, we are a decade away. So today, if you ask someone in the ML community what's the best general purpose classifier, you might get wildly different answers depending on what they have used. But if you want to apply ideas from machine learning in the wild, think about boosted decision stumps if you don't want to think about your problem. It ends up being good, and this is actually also borne out in the industry. Some of our students, including Gianni, who's a TA, was an intern, and a lot of industry ML applications end up using boosted decision stumps. So it's good to understand this idea. And in your homework, you'll be implementing a different kind of an ensemble of decision stumps. You won't be using boosting, but you'll be ensembling decision trees using SVM. So this is a good time to talk about ensembles. The general idea of an ensemble is the following. Ensembling is a meta algorithm that combines the outputs of multiple classifiers. You have a committee of classifiers, and somehow the predictions of this entire committee are aggregated to get a final result, final prediction. And ensembles tend to be quite robust empirically because they reduce variance of prediction. For example, about a decade back, there was the Netflix challenge where they released a data set of movie predictions, of movie ratings. If this person liked this movie and that movie, what would they rate a third movie? Things like that. And the name of the team that won the challenge was called the ensembles. Because it was a massive ensemble of multiple sub-classifiers, and even the sub-classifiers themselves, some of them were ensembles. So, one ensemble idea is called is boosting. We just saw that. You initialize by weighting all examples equally, and then you train a model on the weighted data set. You compute the weighted error, and you increase the weights or decrease the weights based on which examples made an error, and you repeat. You might require hundreds or maybe dozens or thousands of iterations, and you return a specific way of combining these weak classifiers, the edge final that we saw. Yes?
Is there a difference if we change the order in which these classifiers are used?
How do you change the order?
I mean, if for one run you use classifier A, then B.
You mean learning
C.
algorithm A?
Yeah.
Oh yeah, it doesn't matter.
It doesn't matter, you get the same result in the
You wouldn't get the same result, but you'll get a similar qualitative.
Oh. So you cannot cross-validate
You
using
can.
the order, changing the order?
I wouldn't suggest that because often that change of order is something that is lost in the noise, something that's lost in the randomness. So, worth trying, but I would not really place my bets on that. And boosting has been studied quite a bit because it came from the theory community, but also it seemed to be empirically useful. So both the theory people and practitioners like this, like the paper the result I told you a while back, boosting is a maximum margin method. It's an additive logistic regression method. We have not seen logistic regression yet, so this may not mean too much to you. The most important thing here is boosting is actually a linear classifier, but it's not linear in the original instance space, it's linear over the weak classifiers. Pretend that your weak classifiers themselves, pretend that your weak classifier was fixed, your set of weak classifiers were fixed, suppose, without using atoms, somehow they were fixed. Your final hypothesis is just a linear combination. You take the linear combination of the weak classifiers and you take the sign of that. So in some sense, boosting is a linear classifier, but the features to this linear classifier themselves are classifiers. That's how it ensembles these predictions. Another ensembling, yes?
Do we train all the weak classifiers separately? Or?
If you use AdaBoost, AdaBoost prescribes how you train the weak classifiers. You start with nothing, you train one weak classifier, it's a sequential method. It's an algorithm for constructing a linear, for boosting. It turns out, by the way, that algorithm is also in a very, if you look at it in a sort of a twisted way, and I can recommend some papers if you want, it's also a multiplicative update method in a bizarre sense. It also minimizes a certain loss function. So it has tight connections to a lot of different learning algorithms. AdaBoost specifically prescribes a sequence of sequential method. Another ensembling algorithm is called bagging. Bagging is short for bootstrap aggregating. It's from Leo Breiman. What you do is imagine it's a very simple algorithm. The input to bagging is a data set and a learning algorithm that can produce a classifier. Let's say you have your data set has m examples. You take your data set and you subsample from that. You sample a set of examples from your initial data set with replacement. So you pick an example, you keep it aside, you put it back in the pot, you again sample one, you do this a certain number of times, m prime times. So you have a different data set that you have sampled from the original one with replacement. You train your classifier on that. And you repeat that many times. You repeat that thousands of times. And so you have thousands of classifiers that have all been learned on different subsamples of the training set. Your final classifier is just a vote. Each one of these classifiers that have been learned, Ci, get a vote on whether the new example is positive or negative. If the majority says positive, the label is positive, otherwise it's negative. Does that make sense? It's a fairly simple algorithm to implement. You can implement bagging as a higher order function that takes a learning algorithm and a data set as an input and produces this collection of classifiers that vote for the final result. Now,
But isn't it, I think I'm missing something, isn't it possible that you'll have n classifiers so everyone gets one vote, or are you going to get repeated classifiers?
no, you'll have M classifiers that are all slightly different. You'll have M classifiers that are all slightly different. Some of them will say positive, some of them will say negative.
Oh, okay, it's the classification that you...
It's the classification. You vote think of every classifier. So here you're creating a committee of classifiers.
Okay, no, I see.
Yeah.
So the votes are equally weighted,
In this case, yes.
and the classifier can be, there's no restriction that it has to be better than.
No, it's there's nothing. There is a lot of theory around bagging, but I think the assumption is that the classifiers are better than chance. I can't recollect the actual theorem here.
We had done a similar thing in voting perceptron.
Yes, in fact, that the voted perceptron is sort of a similar thing, except it's not taking bootstrap aggregates. This style of sampling is called bootstrap aggregating. It's called taking bootstrap samples. You take bootstrap samples and train a classifier. In voted perceptron, it's still an online sort of thing. And the final idea is actually similar. You get a bunch of classifiers, you remember all of them, and each of them gets a vote. Yes. You can use this for classification or regression. If you're doing classification, every classifier gets a vote, and if you're doing multi-class, you can use for plurality. If you're doing regression, then you just take the average. Every the predictor that you train, these M predictors are all functions that take inputs and produce numbers, real numbers. You take the average of them, and that's your prediction. It turns out there are many different versions of bagging, but the point that I wanted to, this is what I mentioned earlier. You take bootstrap replicates of the training set. That just means you sample the training set with replacement. That's why it's called bootstrap aggregation. Okay, it turns out that there's a lot of experimental evidence that shows bagging is also pretty robust. Again, it sits well with this idea of ensembles generally being more robust. A kind of situation where ensembles and specifically bagging is useful is if your training set is not stable. What that means is, say you slightly perturb the examples. Let's say your examples are points in some space. Let's say this point here. And let's say if you slightly perturb it, and by just making slight perturbations, if your trained classifier, not the ensemble but the individual classifiers have a massive difference, that means your data set is not stable. And in such situations, you can kind of induce stability in your prediction by using an ensemble method. In a classic example where bagging is used, situation where bagging is used is for decision trees. You take a bunch of bootstrap samples of the data, bootstrap replicates, that is examples, subsets of the training set with replacement, and you train decision trees. Yes?
I don't know what you mean when you say the data is unstable. I don't know what that.
It's not. It just means that your data is not your training. The classifier that you learn with your training set will change drastically if you just flip the labels of one of the examples. Let's say it's strongly dependent on a small number of examples.
So you're saying it overfits?
Yeah, basically.
Okay.
But there might be noise in the data. If your training set by just slightly moving it, you get the label changes, that in some sense that means there's noise, and one way of dealing with noise is averaging.
So in this method, why do we take only, we have a big training set, but we only take a part of it for training?
Yes.
Why don't we use the whole training set?
Because if you train twice on the whole training set, you get the same classifier. You want slightly different classifiers.
But we're using different classifiers every time. The CIs.
They are different classifiers, but the same learning algorithm. If you run the same learning algorithm twice on the same data set,
Okay.
you'll get the same classifier. So just as an example, we don't talk about regression in the class, but here's an example of how you can use bagging for regression. Imagine these trees were regression trees. What that means is the leaf of the tree is not a label but a number. Then, and let's say you train all these many trees with bagging, you just average the prediction. Let's say each of these is the output of one of these trees. You average the prediction of these trees, and the final output is the average of those things. So sum of those divided by the number of trees.
Is there a rule on the size of your subsets?
Oh, good question. What I would do is cross-validation. Again, like you're laughing, but every time there's a difficult question, I say cross-validation. So let's introduce this idea of random perturbations to the data set a little bit. And let's kind of push this idea of random perturbations a little more. For bagging, you took a data set and you subsampled a set of examples. Random forests takes this idea and runs with it. Not only do you subsample a set of examples, you also sample a set of features. You don't use all features, you use a subset of the features. And so you now, let's say this is your training set. Every row here is an example. And let's say this is a label, the last column. For bagging, what you do is you just took subset of the rows. You took this row and maybe this row, this row and this row and this row. That's it. In random forest, not only do you take a subset of the rows, you also take a subset of the columns. You say this feature is not interesting. This feature is not interesting. And you take only a subset of the features and you train a classifier. And you repeat the same thing. Yes?
Do the features also get replaced as you train?
No,
you only pull the pull the feature out for each.
For each bootstrap replicate, you take a set of examples and you decide once at the beginning, for this particular classifier, I'm going to use feature number 1, feature number 3, feature number 18.
But those don't get replaced in the next train.
And then you put it back in.
Okay.
And then you repeat the process. So I saw your hand and then you, yes.
So when you decide which feature to select, is it a random
It's
choice?
random. It's random.
So bootstrap replicate is our new term for weak sublearning now.
No, bootstrap replicate is the training set. Is a sub-training set.
Okay.
Yes.
So the features themselves are random. Is the number of features that you select random as well?
Oh no, you can play games there. Let's pretend that for simplicity, let's say it's not. You could do that, and then you could put a Poisson distribution on that, but then Poisson has a hyperparameter, then you can make that a random variable, and that's how you become Bayesian.
So it's a lot of cross-validation.
No, the idea is you reduce cross-validation by treating things as random variables. I'm not saying being Bayesian is bad, it's sometimes a good thing. Yes?
How is this different from a neural network with a hidden layer?
It's actually very, very similar. You can think of a neural network with a hidden layer as an ensemble. A neural network, a two-layer neural network, we haven't covered that yet, but since you asked the question, you can think of a two-layer neural network as an ensemble of linear classifiers. Alright, so let's wrap up this thing. I'm at least 40 minutes late today because I wanted to start SVMs, but let's wrap up ensembles. I started this story by talking about a question from learning theory. If your concept class is weakly learnable, doesn't mean it's strongly learnable. And the answer to that question is yes. And the proof was constructive in the form of an algorithm called AdaBoost. But AdaBoost is an instance of a larger family of a larger idea of learning algorithms called ensembling. And ensembles is a really important idea that you should feel comfortable with when you're using machine learning, because sometimes, especially if you care more about getting the actual answer and not so much about publishing papers, for example, you might want to think about ensembles because it ends up giving you robust classifiers. And AdaBoost is just an instance of an ensemble learning method. In general, the idea of an ensemble algorithm is ensembling is a meta learning algorithm. It takes a learning algorithm and a data set and somehow constructs many classifiers and also proposes a way in which these classifiers can be combined. A natural way of combining the outputs of classifiers is voting. But another way of doing that is to treat the prediction of each of these classifiers as a feature and train another classifier on top, which is what you're going to do in your homework. You're going to build a linear ensemble of decision trees. You're going to train an SVM by pretending that the predictions of your decision trees that you train are features, and you'll train a linear classifier on top of that. Was there a question?
Yeah, I hope I'm not belaboring the point or slowing things down. But just to clarify mechanically what's going on with this random forest of egg trees. So you have all your data. You partition that into a bootstrap replicate.
You don't partition it. You sample a subset of examples with replacement.
Okay, sample with replacement in the bootstrap replicates. And then in each of those replicates, I grow a forest of...
Using only a subset of the features.
Yeah, yes. And so for each replicate, you have a collection of trees, and each tree only regards some of the features.
Yes, that's right.
And so then within that replicate, you're kind of constructing a like a boosted set of trees.
Within each round,
Yeah.
you just construct one tree.
One tree.
You construct one tree. You have a
Okay.
set of examples that have been chosen with replacement, that have been sampled from the training set.
Okay.
You have been told that for this particular round, the learning algorithm is only allowed to use these features.
Okay.
And you train one tree. You grow a tree for that data set.
Oh, okay. One tree per round. Okay.
And if you run this t times, you have t trees.
That's the forest.
That's a forest. Yes. By definition. A forest is t trees. Yes.
Should we pick subset with the same size at different bootstraps?
Typically, that's what's done. So, let's say you do that. And you can also do other things, like you don't have to grow full decision trees. You can grow decision trees, depth limited decision trees. Limit the depth to, say, size 3, for example, which means each individual tree is not going to be particularly great, but there's some theory that shows that the ensemble will be better than any one of them. Alright, so now let's switch tracks and go to support vector machines. Just to give you an idea of where we are, we've seen a bunch of learning algorithms since the beginning of the semester. We've seen decision trees, we've not seen nearest neighbors. This is an old slide that should have been fixed. You'll see nearest neighbors at the end of the semester. We've seen perceptron, winnow, we just saw AdaBoost and the idea of ensembling. Some of these are linear classifiers. Perceptrons, winnows, and AdaBoost produces linear classifiers. We've seen general ideas in machine learning. Again, this is an old slide, we've not seen the curse of dimensionality yet, but we've seen the idea of overfitting. We've asked ourselves, what does it mean to learn? And one answer to that was learning means the learner stops making mistakes, and that gives you your mistake-bound learning. Another way of answering the same question is, learning is defined in the PAC formula, under the PAC framework. And that gives you these ideas of sample complexity and VC dimensions, and how do you choose hypothesis spaces and stuff like that. And we spoke about the difference between training and generalization error. These are general concepts of machine learning that can be used to applied to not just the specific settings that we saw, but more broadly. And my hope, by the way, is that given that machine learning is a very broadly, very quickly growing field and also pretty vast. I can't cover everything, but these general principles will help you reason about new algorithms that you might read, papers that you might see. Coming up, we're going to go back to another question, actually another way of thinking about linear classifiers, this time motivated by a result from learning theory. In fact, motivated by something that we've seen about VC dimensions. And this will lead us to this very broad and probably the dominant idea of creating learning algorithms called the principle of risk minimization. And once you come to the risk minimization principle, it gives us a recipe for constructing learning algorithms by combining this with, say, something like stochastic gradient descent. So you transform the problem of learning into an optimization problem, into a real continuous optimization problem, and any algorithm that solves continuous optimization now, it becomes a learning algorithm. And that's why you see, for example, these days if you see in papers, you don't see learning algorithms, you see objectives. I want to transform my learning as this, minimizing this objective, and you transform your learning into an optimization problem and just say we use stochastic gradient descent, which is why you should pay attention in the next class. But let's get started. Before, just to kind of remind you of the big picture, we spoke about linear models, linear classifiers, and we simultaneously asked the question, what is a good learning algorithm, or how good can learning be? We spoke about online learning, and combining online learning with the idea of linear classifiers gave us perceptron and mirror. We saw pack learning and agnostic learning, and combining linear models with pack learning is going to give us support vector machines. There are other ways of asking the question of what's a good learning algorithm. In particular, we'll see one more, the Bayesian approach, and that combined with linear classifiers will give us naive Bayes and logistic regression. But we'll see that maybe in a few weeks. So now I'm going to talk about support vector machines. The fundamental, the most important idea when it comes to support vector machines, conceptual idea, is the idea that learning a linear classifier should be done by maximizing the margin. So the margin that, you remember the margin that we saw with perceptron? When we spoke about the perceptron bound, the gamma? We're going to try, the intuition behind support vector machines is that it's a good thing to maximize the margin. I might have said minimize. It's a good idea to find the linear classifier that maximizes the margin. And the idea of maximizing the margin directly leads to the SVM objective, and the SVM objective is an optimization problem, and that will lead us to the SVM. There are many, many different ways of solving that optimization problem. One of them is stochastic gradient descent, and my hope is today at least I get somewhere in the middle of that section. So let's get started. Let's start with learning with the idea of maximizing the margin. So let's go back to VC dimensions. You've seen this before, so let me just repeat this though. Let's say this is in the context of agnostic learning. For agnostic learning, we said the true error, the error D of a hypothesis, if you have M training examples, then with the epsilon delta bound, with high probability, the training error, the true error, is bounded by the sum of the training error and some massive function of the VC dimension. But the general intuition is that we had was, if you have lower VC dimension, then you get this, the thing inside the circle becomes smaller, so you get a tighter bound, which means it's a good idea to minimize the training error plus this function, because then if you minimize the sum of these two things, then you get a low generalization error. Completely different thing that we also saw was that the VC dimension of a linear classifier in D dimensions is D plus 1. For, in fact, for hyperplanes, for lines in 2 dimensions, I proved it in class. The VC dimension of a linear classifier in 2 dimensions is 3. So we can plug this in. We can, let's think about what this means for linear classifier, what that big expression means for linear classifier. You can just plug D plus 1 here, and we get some number that's independent of everything else about the classifier. the question that brings up this discussion about margins in support vector machines is, are all linear classifiers really the same? So let's look at an example. But before that, let's think about this. I'm going to ask you a question, but to answer the question, I want you to think about the idea of margins. So to remind you of margins, if you have a data set and a hyperplane, the margin of the data set with respect to the hyperplane is simply the distance of the closest point to that plane. Just, I hope you remember that this formula for distance between a point and a line. We'll be using that quite a bit. So now, I want you to answer the following question. Suppose you have this data set and I have two different learning algorithms. One of them produces hypothesis H1, another one produces hypothesis H2. And this picture also shows you their margins. Which one of them is better? Why? So what? Some of you said margins bigger, but so what?
Less generalization.
Why?
Because there's more to play with, even if it goes inside the margin, it's still the right play.
That's right. Was there a hand? Did you raise your hand?
I was just going to say roughly the same thing.
Okay.
So there is more possibility for error
There's more possibility for.
in case of new symbol is somewhere closer to the
Right.
market.
So all three of you roughly have the same answer. Let's say that a new example comes in. That's not in the training set. There is more room for H2 to place the new example here. This is just proof by pictures, but it's not valid math. But I'm just giving you an intuition. There's more room on the positive side of the hyperplane for this new example to show up. On the other hand, if the margin is smaller, there's a higher probability that the new example will get misclassified. This is, again, just proof by pictures, it's not valid math. But does the intuition make sense? There's more wiggle room, in some sense, for the classifier that has the larger margin. It turns out, yes.
So are we saying there's no noise on these examples again?
No, we are, for at least maybe a little bit of, for next maybe 10 minutes, let's pretend there's no noise.
Okay.
But eventually, we'll deal with the noise case as well. In general, the intuition here is that larger margins are better. And the way to formalize this intuition is to think of data-dependent VC dimensions. So far, the VC dimension that we had was only a function of the hyperplane, of the hypothesis class. But suppose you have linear classifiers in D dimensions. I'm going to partition them, or not partition them, but let's say I'm going to take two subset of all possible lines in D dimensions. One of them, for a particular data set, is the set of all linear classifiers that has margin gamma 1. Another one, so if you have a data set plus and minus, let's say gamma 1 is maybe this number here. This is a linear classifier, this is gamma 1. This is another linear classifier, let's say this is gamma, I hope that's too close. So this is another linear classifier, this is gamma 1, and so on. We are considering only lines that have margin gamma 1. That's a set of functions, right? And so that makes it a hypothesis space. Let's consider a similar hypothesis space, a set of all linear classifiers that have margin gamma 2. And now let's say gamma 1 is more than gamma 2, meaning gamma 2 consists of all points that, let's say, go very close to the training examples. Something like this. So I'm removing the first one. So this is gamma 2 here, this is gamma 2. So gamma 2 consists of lines that are closer to the training examples in some sense. So that's another hypothesis space. Intuitively, the set of functions h1 which have margin gamma 1 is better than the set of functions h2. So now the question is, can we formalize this in terms of VC dimensions? Because if we can do that, then we can actually start making some formal claims. Turns out you don't have to do that. Rapnik did that a long time back. You can there's a notion of a data-dependent VC dimension for linear threshold units. Suppose you have a data set where all points are within a radius of r, and let's say all these points are in d dimensions. This theorem says the VC dimension, and now consider the hypothesis space of all linear classifiers with margin gamma. Theorem says the VC dimension of this is the minimum of r square over gamma square plus 1 or d plus 1. Now let's assume that d is very large, just to make life easier. So it's really, the VC dimension of this is something like r square over gamma square. What that means is that if gamma becomes very large, the VC dimension becomes very small. If gamma is very small, VC dimension is very large. This means for a particular data set, if you have multiple hypothesis spaces, all defined by, multiple sets of linear classifiers, each of which is defined by a particular margin, you should choose the one that has the lowest possible margin. That makes sense? Because that gives you lower VC dimension gives you better sample complexity, lower VC dimension gives you a better bound on the generalization error from the first slide that we saw, that theorem that we had. You seem perturbed.
Yes. So you're saying we want, in order to get lower future error, we want to have a smaller margin?
Larger margin, lower VC dimension.
Larger margin, okay, we're good.
Yes, yes. So this is a somewhat formal statement of the idea that larger margins are better because they might minimize future error. Yes.
Didn't we before classify the higher VC dimension? That was more expressive.
They are more expressive, but the sample complexity is high. If you have higher VC dimension, the number of examples needed to make the same kind of epsilon delta bound is higher, and if you look at the expression here, higher VC dimension means this bound. So if VC dimension is high, this quantity becomes higher, this whole thing becomes higher, which means your bound on the training error, on the generalization error is weaker. So your generalization error might be large. On the other hand, if the thing inside the box is small, then your generalization error is not going to be too much worse than your training error. So lower VC dimensions, better generalization. Yes?
How can we justify having our VC dimension dependent on our data?
Why not?
It's just okay?
It's fine.
I suppose none of the things it feels like when we did the proof of, it used like the hefting balance.
Oh, that's right.
and such,
That's right.
it depended on not knowing what our sample was.
Yes, in this case, you're right. This is actually qualitatively and quantitatively different. It turns out it's the same sort of idea. Formally, it's the same. Mathematically, it's identical, except this requires a lot more heavy lifting. That's right. The idea is the more important point is you're not using the data points themselves. You're using the hypothesis, you're using the data to only define the margin and this R square. You're not actually using the identity of the points. So it's fine. Alright, so the argument here is lower margin implies lower VC dimension. Lower VC dimension implies better generalization. So here's a recipe for training. Find linear classifiers that have low margin. And that's the entire idea behind the support vector machine. Support vector machines they are a set of classifiers that have been trained to minimize margins. That's going to give us our learning strategy. Okay? So, but that's just a vague idea. Let's try to make this more formal. How do you maximize the margin? In order to do that, we need to think of the geometry of the linear classifier. There's actually a subtle bit of there's one subtle argument that's coming up. So you might want to switch into this geometry mode zone. Remember that the linear classifier divides the space into two parts. One side is positive, the other side is negative. What is the margin? The margin is simply the distance of the nearest point. And you remember the formula for the distance. The distance of a line from a plane is simply, if your line is W transpose X plus B equals 0, if that's your hyperplane, the distance of a point from the line is the absolute value of W transpose X plus B divided by the norm of W, the length of W. And this is the same thing here in 2 dimensions. But we have a little bit of freedom here. We don't really care about the actual distance, we only care about the sign. We only care about the sign of W transpose X plus B, not about the actual value of W transpose X plus B. What does that mean? It means that as far as the classification is concerned, all these three are going to produce the same result. Right? The sign does not change. The actual value of W dot X changes because the W dot X here is twice the W dot X in the first one. Right? So we only care about the sign. So, does that make sense?
Yes.
Okay. It also felt good. There's some music to support the argument. It's always nice to have a soundtrack to your life. Now, remember that the margin is the distance of the closest point to the hyperplane. You have, now your points are xi, yi. So I said the margin is the smallest value. So the distance of the point from the plane is absolute value of W transpose X plus B divided by the norm of W. If you have training set xi, yi, the margin is simply the minimum value of that, so minimum over xi. Right? But suppose W and B, the hyperplane, correctly classifies the training set, because that's what we want to find. Let's characterize what that would look like. If it correctly classified the training set, then for all training examples, this quantity is positive. Yi times W transpose X plus B is greater than 0, right? Which means this quantity is exactly the same as the absolute value of W transpose X plus B. Make sense? If W transpose X plus B is positive, then this quantity is positive and so is Yi times W transpose X plus B. If W transpose X plus B is negative, to take the absolute value you need to multiply by minus 1. Do you have a minus 1 lying around? Yeah, it was negative, so Yi was minus 1. So this what we care about, the margin, is exactly the same as this thing here. So we want to find, so here's a learning algorithm. We want to find, or here's a learning strategy, and I'm going to say it, but I'm going to also tell you that it's not easy to solve directly, which is why you need to do a little bit more of math. But this is the margin, gamma, is the margin. I'm going to put gamma W, let's put gamma W here also, is the margin of the weight vector W and B. Right? I want to find the parameters that maximize the margin. So I want to find goal. The goal is to find W and B such that that maximizes gamma WB. Right? So that's your learning strategy. Find the W and B that maximizes the value of this quantity. Which quantity? The minimum of the closest distance to the hyperplane. So minimum of xy, y W transpose x divided by norm of W. So in the literature you will see phrases like geometric margin and functional margin. The geometric margin is actually the distance that you see. The functional margin is just the numerator. The functional margin is the geometric margin when you use a unit vector for the weight vector. Okay? Just names. Is the strategy clear? Is what we want to do, does it make sense? Yes.
Is there any mathematical convenience for using B
No.
outside the weight vector?
No, there isn't. I just wanted to remind you that there is a bias. We are still in the space of linear classifiers. And also sometimes in the literature you will see this, so I want to kind of get you familiar with this notation as well. Okay. But this is an optimization problem, you know. What is an optimization problem? Minimizing and maximizing functions is optimization. Gamma WB is a function of W and B. So it's an optimization problem, but it's kind of a painful optimization problem to solve as is, because it's minimizing this quantity, maximizing the minimum, so it's painful. So it's even painful to write, so I'm not going to bother. But there is a little bit of trickery that we can use to make our life simpler. And the key point is that we only care about the sign of the prediction, not its sign of the dot product, not its magnitude. Which means, now pretend, suppose I am able to find, you remember I had 2b plus 2w1 x1 plus 2w2 x2 equals 0. That's the same line, right? Now suppose I am able to find some constant alpha, positive number, alpha times b plus w1 x1 plus 2. Suppose it's the same line. If alpha is positive, you agree it's the same line. Right? So, suppose I try to find an alpha such that the actual distance of the closest point is the number 1. Sorry, not the actual distance, but the numerator is the number 1. So, I want an alpha such that for this particular point, let's call this x1, x1, x2. This point here, suppose I knew the closest point, and I want the closest point to be at a distance of 1, to have a functional margin of 1. What does that mean? The numerator of this quantity should be equal to 1. In other words, the distance of this thing, the margin, I want the margin to be 1 divided by I want the distance to be that. So can I find an alpha such that the margin becomes this quantity? Can you tell me an alpha such that the margin becomes that quantity? If I knew that particular number, let's actually give this number, give this point a name. Let's call this x1 star and x2 star. I'm using x's and stars, which is very similar. So let's say that this point is fixed. Let's say you knew that point. Can you find an alpha?
But I'm on mod of p equals w1.
Say that again?
1 divided by mod of...
Exactly. So if I pick alpha equals 1 divided by, in this case, absolute value of b plus w1, x1 bar plus w2, x2 bar, what will happen? When I'm calculating the distance of this point here, the norms cancel out, and you're left with this what we need, right? You can basically scale the points, you can scale the weights up and down so that the closest point is at a distance 1 over root of w1 square plus w2 square, because you have this degree of freedom. You don't care about the value, you only care about the sign. You can scale it up and down so that the closest point is at a distance 1 over root of w1 square plus w2 square. Does the intuition make sense? I mean, do you agree that that's possible?
Well, but if you're just changing, the 2b to 1000b, it's all the same line, so how are you changing the actual geometric distance?
The distance doesn't change. The numerator changes. Only the numerator changes. I'm setting the numerator to 1, so I have this degree of freedom where I can multiply by a constant so that the numerator becomes 1. The distance remains the same, you're right? Okay. And similarly, also for just to remind you that there's also the negative. If the point is at the closest thing, the negative examples are also, the closest negative example will also be at the same distance, because you'll put the line in the middle. So, what does this mean? You want to maximize this quantity. But, instead of maximizing that quantity, what you will do is set the score. I prefer using the absolute score rather than functional margin. Okay, so I'll end up saying score. Set the score of the closest example to be 1. Find a W such that I want to minimize gamma W. I'm not going to write the bias. 1 over norm of W, because if for closest point yi and let me put the b also is greater than is equal to 1. That make sense? If the closest point had yw transpose x, that is the numerator equal to 1, that is if for the minimum, the argument, the special point that was chosen to be the closest, if yw transpose x is equal to 1, then this problem of finding the margin of that weight vector is exactly 1 over norm of w, if the numerator is equal to 1. And you have this freedom of letting the numerator be equal to 1 because you can scale w up and down. So that means you maximizing the margin is equivalent, and I want to find the w that maximizes this quantity on top, the 1 over norm of w. But maximizing 1 over norm of w is the same as minimizing the norm of w. So here's the new recipe, which is equivalent. Instead of maximizing the margin, I'm going to minimize the norm of w such that the closest point has an absolute score of 1. Questions at this point? Feel like your silence is a little worrisome. Yes?
So basically what we are doing is the formula we had earlier, we are just making the numerator 1
Yes.
first, and then our weights would have scaled by now,
Yes?
and we are minimizing the norm
Of the
the
scale weight.
of the scale weight.
Yes, exactly. That's perfectly right. Other questions?
What about being here? Weight?
Oh yeah, there's a B. There's always a B. I mean,
So setting it to 1 just because
it's a mathematical convenience.
I was going to say that just makes it easier.
Yes.
That's the point.
Yes.
Okay.
But what does it mean to set it to 1? And this is probably the last thing I'll do now. What does it mean to... Effectively what you want to do is minimize the norm of W such that the closest point is at a distance 1. But how do you set this to 1? You frame it as a constraint. If the closest point is at a distance 1, then every point should be at a distance more than 1 over norm of W. So, here's the learning problem. Minimize, instead of minimizing norm of W, I'm going to minimize W, so I can minimize the norm of W square, because I can take derivatives. So I want to minimize the norm of W square such that closest point has score or absolute score equals 1. But instead of minimizing the norm of W square, I can minimize the norm of half W square, because when I eventually take derivatives, the half will disappear. But what does it mean to say that the closest point is that has a score 1? This means that this thing is equivalent to saying every point has absolute score greater than or equal to 1. The closest point is has a numerator 1, every point has a numerator more than 1. But what was the numerator? The numerator was simply yw transpose x. Exactly. Right? And that I want it to be more than or equal to 1. That gives you the, so this is the same as this. Everything in the box is the same. So this is the same as, so this leads to this, and this is leads to this, and this is exactly the same as this. So I want to minimize the norm of W. In other words, I want to minimize half W transpose W such that yi W transpose xi greater than or equal to 1 for the entire training set. This means this condition is true for all examples. I mean, the constraint is true for every training example. In particular, it's true for the example that's closest to the training set. Actually, the equality holds for the closest point.
What is a B?
Oh, I got rid of all the B's because I assumed that the B goes into the feature set. There's always a bias. Yeah. So this optimization problem is called a hard support vector machine, and by hard it doesn't mean difficult, it means it does not account for noise. So far we are assuming that there is a classifier that perfectly classifies the data. So there's a hard separation between the points. We'll look at how to solve this optimization problem next. Actually later, the next lecture, Shingwan is going to cover the case where the data is not linearly settled, and that gives you the soft SVM, or what we just call SVMs. Reminder about all the announcements: there's a homework due today, there'll be another homework available tomorrow. There's a project with intermediate report that needs to drop on November 8th.